just a short recap of where we were. So we've been looking at sort of using monads to give semantics to programming languages. And last time I went through, in some amount of detail, something called the free monad, and this idea that we can sort of parameterize a monad by a notion of events and then have handlers that sort of separate the sort of syntactic parts from the semantic parts. And just at the end of last time, we finally arrived at this concept of I-trees, which are pictured here. And I'll go through that a bit more. But basically, the idea behind I-trees, interaction trees, was that we're going to combine sort of two things. We're going to combine this notion of the free monad, which is a structure that is parameterized by a type of operations or a type of events. We tend to refer to them as events in the I-trees development. And something called the delay monad, which is basically a monad that lets you potentially go into an infinite loop. And the way that we realized that in Coq was via this co-inductive data type. That has this E parameter, which describes the shapes of the nodes of the tree. The result type R is just a standard monad parameter. And then there are three constructors. The ret constructor is just the pure return. The tau constructor stands for these sort of silent steps of communication or of computation that just wrap a tree. They sort of let us delay a little bit. That's why the delay monad gets its, where it gets its name. Tau is sort of like delaying the computation just a little bit. And then these viz nodes, visible nodes, which have the shape of one of these E event objects as the structure of the node. And then for each possible answer here given by the type X, a function, a function that tells us for each possible answer what the tree given that answer is. And so pictorially, we saw they look like this, where the sort of pink taus are those tau nodes. These blue or teal squares are the events. And then the return constructors would be sort of the leaves of these trees. So that's the picture. And we didn't really get too much into using this for very much. So we're going to pick up today with sort of writing programs that use I-trees and then thinking about equational reasoning of the style that we've been looking at all along. But before I get into that, are any questions about kind of just the basic ideas so far? Yes, question?
So one motivation was that you wanted it to be executable?
Yes.
Are you able to execute one step only, or can you?
Oh, right. So the way in which these I-trees are executable in the sense of, so in contrast to, say, the propositionally defined semantics is, these are just data structures. And if you use a co-inductive data type like this in Coq and you extract it to OCaml, what you'll get actually is a lazy tree that has exactly these three constructors. And when you force the tree, it will give you the next node, and then you can do that. So to extract, and we'll see a little bit more about this, to extract a sort of an interpreter built on top of this, basically there's a little bit of work that has to be done to just keep forcing the tree, but that's it. So in some sense, the interpreter is just explore this tree, but it's completely extractable in that sense. Yeah.
So when you say it's executable, that means only with extraction to OCaml, not like within.
Well, I'll say a bit about how we think about this in Coq. So the question is, when I say it's executable, what does that mean? In Coq, you can't, of course, just run a computation that will go into an infinite loop. So that just is it's a non-starter. In practice, there's lots of ways you can get around it. So you can write, if you want to shift to the fuel, in fact, I'll show this later. If you want to shift to the sort of fuel version, you can force, any finite amount of computation. That works just fine if you have a bound on how many steps you need to force. But in practice, actually, when you're doing proofs over these things, you typically don't really think about executing them in that sense. You sort of explore the tree by inspecting the constructors. And when you do a co-inductive proof, at some point you may realize that you've already handled the case you're looking at and be able to conclude your proof. So from within Coq, you can't just straight up run an infinite loop, of course. And then we have some, I guess there's sort of another piece of this is when you're doing actual proofs that involve these structures, you can write a tactic that will sort of normalize them a certain amount, which is useful for effectively running them for the purposes of the proof. So when I say executable, I mainly mean that you can still extract a program and run it in OCaml and get something that runs perfectly well and even reasonably performant. Tomorrow, hopefully, when we're sort of wrapping up, I'll show you our Vellum semantics, which is built on top of all of this, can easily run relatively big LLVM programs through an interpreter extracted in this way. Good. So let's see how we would get to something like that, though. So just a couple of examples. So just Steve was just talking about how to do a lambda calculus with I/O events. We could build I-trees with I/O events like this. So we might have a type of I/O events where, say, we're outputting natural numbers, and the environment doesn't return any interesting results. So the result type of this is unit. And if we read from the environment, we get a natural number. So these are sort of, we can output natural numbers to the environment and input them from the environment. Well, let's look at some trees. My French colleague likes this tree that just returns 1789. It's a pure tree. It doesn't actually do any I/O. It just halts immediately. But here's a slightly more interesting tree. It's an I tree. It reads. So the way I like to read this is, so this is building a tree whose root node is an input, and whose continuation says, well, when the environment tells us what natural number was provided for this input query, we're going to return twice that number as the leaf of this tree. Here's a little, we can just program in Coq using its co-inductive data types. So here's a tree. It's an I tree, also does I/O events. This one goes into an infinite loop. So it does the same thing. It prompts the environment for an input. Whatever n it gets, it just echoes back out using this output event. And then the continuation, which doesn't get any interesting input because it's a unit result from the environment, just goes back to echo. So you can think of this as a tree that denotes, essentially, while true, input a number and then output that number and then forever do that. So going back to that picture, that might be something like this, where instead of just E3, we would have sort of input, output, input, output, input, output forever. Okay? So those are a few trees we can just write by hand. And the game we're going to play is now we can build semantics by creating these kinds of trees and interpreting them kind of the way we did with the free monad. The couple of special trees, the all tals program, all tals tree, we can actually give it lots of different types. So here's one type. We call it spin specialized to these I/O events. And this would be sort of the tree of all tals that claims that it might do I/O, but it doesn't actually do any I/O. But actually, we can make a very generic version of that. Spin is just tau spin. And that's true for any event type whatsoever, because it doesn't do any, there are no sort of real nodes in this tree. And for any result, because there's never any return, it's just taus forever. So this, in some sense, is like morally the bottom. If you're thinking of sort of a semantic lattice, it doesn't have any observable behavior except that it goes into an infinite loop. Cool. OK, so there are a few other games we can play. I mentioned that since these events carry their event type, the type that they're reading from the environment as an index, we can make an empty event like this. So all it does is say that the result from the environment is the void type. And there can be no continuation for a void type because there's no way to continue from that. And so this is one of these orange nodes. It's an event. It's visible in the sense that the outside world can see it, but there's no way the outside world can respond because it's supposed to respond with an impossible empty type. And the nice thing is we'll see that actually I-tree equivalence will make distinctions between returns and void types, events, and so on, which is quite fine-grained, but that gives you sort of choices with how you model interesting computation systems when you're using these things. Great. So as an example, here's a tree that we just call fail that just is one of those orange boxes, has an empty node with, this is the way you could write a continuation that, that takes an X. It has sort of any type at all that you like. It eliminates the void. Just as for the free monad that we saw last time, we can define sequential composition of these I-trees in exactly the same way with exactly the same intuition. It's a little bit slightly different to write because of the way Coq wants to check that we always have a sort of guarded recursion. We have to write it in this way where we're trying to sequence, let's read how this works. We're trying to sequence one I-tree, so U before some continuation K. So the type of U here is an I-tree whose return leaves carry the type T. And then K is takes a T and builds a tree of type U, returning with leaves of type U. And basically what this sequence operation does is it crawls over the tree. Every time it finds one of those purple return nodes, it just calls the continuation. When it hits a tau, well, it just keeps searching for leaves. It goes under a tau. If you think about it, because this is co-inductive, if we have an infinite stream of taus, this sequencing operation will just keep pushing the sequence further and further along, and that's why it's sort of a lazy data structure. We couldn't build it all at once, but we can explore it dynamically, lazily. And for these visible nodes, well, we preserve the node at the root of the tree, and then just sequence the same, which includes its handler or includes its continuation H. We just continue the sequence looking for the leaves that appear under that function. So that's all there is to it. The one trick is that compared to what we saw before, we have to write this cofix slightly. Coq wants us to consume this co-inductively defined tree U after having seen this parameter K, just so that it makes it easier to check that we're always sort of stepping past one of the constructors of our tree before doing the cofix point. So that's just a little wrinkle with how Coq expects us to write these kind of co-inductive functions. But really, it's the same exact intuition. We're crawling to the leaves and then calling this continuation on the leaves. In fact, that is the bind of the monad. The only thing is that since we wrote it with the sort of parameters in the opposite order from the way that I defined the type of bind, we just flip the order. So the way that I wrote the type of bind, we take an I-tree and then the continuation, the body of the bind, and so we just call this like so. And we can play the same game that we did with the free monad and have a trigger kind of convenient syntax, which just takes one of these events, E, and kind of lifts it into our I-tree as a node that immediately just returns its value. So this is sort of a minimal tree that just has the node E and nothing else. Well, E plus a return for where we can glue on more trees. Okay, so hopefully after seeing all the free monad stuff, this is pretty straightforward. But please do ask questions if you have any. Good. Okay, so here is I started off on day one saying, well, it would be great if we could write a denotational semantics for imp, but we can't because we can't write the case for the while loop because we don't have a way to handle divergence in Coq. But the one thing that we can get that we couldn't get before, now that we have I-trees, is a notion of potentially infinite iteration. And so this is a useful combinator. In fact, we, again, will, I'm not going to dwell on it too much, but we make a type class that says monads that support iteration need to have an operation whose type looks like this, where I've specialized this one to I-tree. So let's step through the type first. So what is an iterator for a computation? You can think of it as like a loop where we start with some initial state of the loop, and we take what the loop is going to do is run a step of computation. In this case, it will be one of these monadic I-tree computations. And the result type is I plus R. And the way to think of it is we're going to get either an I or an R. And if the loop body says, oh, here's the I, that means go back to the start of the loop and iterate again. So another way to think about it is this I is the sort of state that's carried through the loop and back to the beginning. And this choice at the end tells us whether we're going to keep iterating or terminate. And if we get an R, well, then we're done. And with that algorithm, so what iter does is it takes this loop body and an initial state for the starting condition of the loop and gives you back the potentially diverging I-tree that promises to deliver an R after the loop is terminated. So, so let's take a look at what the code does. It's actually pretty intuitive. What we do is we start with our initial state. So we're given our initial, so init here as type I. We run one step of this iterated computation. That's going to give us this LR. So either we're going to go left and reiterate, or we're going to go right and terminate. And in the case that we go left with the updated state, well, here's the thing that we have to do. We have to take a tau step, which is one of these silent, we have to mark that we did some work in our loop. Otherwise, it would be considered non-terminating from Coq's point of view, not well-founded co-inductive function. But if we sort of mark that we did some non-trivial work, we can just call back into our iter with this cofix. We're allowed to reuse our iter with this updated state. So this is the case where we decided to re-enter the loop with a new state. And then otherwise, we just return the result. And you'll notice that here I'm actually using the bind of the I-tree. So this is this overloaded notation. So really, we're doing all of this in this I-tree type. So intuitively, we're building up this potentially infinite tree where one way we could continue to build branches deeper into the tree is by going around the loop via this iter. And it might potentially produce an infinite series of taus, like if, for example, the step was just give me the initial state, and I'll return in left of that initial state. That's like while true, do skip, essentially. Question, yeah?
Could you also make an assumption that instead of this type I, it takes this type I plus R, so the loop has the option to?
Sure. So the question is, could we have started with an I plus R and done similar logic? Yes, there are quite a few variants on these, and you can write other loop combinators. This one we pick because it has a category theoretic notion that I'll show you some laws once we get to equivalence that sort of justify why this is a nice way of thinking about things. But you can just write, yeah, there are other choices as well that would work. Good. OK, so that's iteration. It's just writing down what looks like a normal loop in any regular programming language, except we have to do this a little bit of using cofix to say that it's building up an infinite tree, potentially. And we could continue to program I-trees sort of manually by hand in Coq, right? So now that we have this, here's an example. I can write this in Coq as a sort of factorial function that takes a natural number. It's not going to just immediately compute a natural number, although factorial is inductive on the structure, so we could do it that way. But we could also, so this is sort of the iterative version of while loops, where we we start with some kind of state, which in this case is going to be an accumulator, which starts out as 1, and the natural number that we're going to decrement each time around the loop. And so what does each step of iteration do? Well, we check the current state. We check whether we finish. So if n is 0, we just return the accumulated value. And otherwise, if n is some successor of m, we will return, I should say, we return in right. I spelled out all the details. The in right here means we're going to terminate, right? That's the right-hand side of our body. So in this case, the body of the iter is, the state is a pair of natural numbers. So it's int cross int plus, and the right-hand side is just the result. So if we kind of look back at the type of iter, in this particular instance, I is int cross int, and R is int. So we indicate termination with in right. Of course, you could make nicer notation, like you could say halt of the accumulator to be sort of syntactic sugar of that. It might look a little bit nicer, or break or something like that. If we want to go around the loop, well, we signal that we want to keep going with updating the accumulator, so n times the accumulator, and we decrement the counter from successor of m to m. And so this will compute factorial as a kind of I tree. Yeah?
What is the tick in front of accumulator?
Ah, right. Yeah. So this is the tick in front of Coq is a little bit. So it's not super important, but in Coq there's something called an irrefutable pattern for data types that have one constructor, like products that have a pair constructor, and you can use the tick to say that I want to do inline pattern matching. It's just a Coq quirk. Most programming languages would let you just write a pattern here directly. Coq wants to know for sure that it's a single case because it doesn't have notation for what to do if there's more than one case for that data type. So you can just read it as pattern matching. Okay, this is actually getting to Josh's question, which is like running I trees as a computation, right? So if you try to use Coq's compute in this to like run that factorial thing, you'll just get a tree because they're sort of lazy, and it depends. You can use call by name. You can force some evaluation, but it won't diverge for you. You can do a couple of things. If you really want to, you can write this function called a burn, which takes some amount of fuel, and all it does is sort of force the tree. So here I'm calling this observe function, which you can think of. I'm eliding a few details about how we actually implement this in Coq, but you can think of this as like forcing the one node of the tree, you know, if we get a tau, we just strip off the tau and force the next node. So this is a sort of fuel-based thing, and if you happen to know that you can burn enough fuel to evaluate factorial of 6, well, that will actually force the computation down to, in this case, the trivial I tree, which is just return 720. Yeah? Yeah?
Couldn't I have an infinite I tree with no towns, like this all this?
Sure. So the question is, can you have an infinite I tree with all vises? And that's also fine. This what it will do actually is it will force it down to the first viz. So it'll stop as soon as it hits a return or a viz. And the reason why that makes sense is because these are trees, right? We're sort of skipping past all the hidden steps, the towels, at least n towels in this case. And then once we have a return or a viz in hand, we can look at it and do some computation on it. Yeah.
So these being lazy, and then you give them a certain amount of fuel to go. Can you use these to build, generators and things like that?
What do you mean by generators?
I guess sort of like a prime sieve, or as an example.
Oh, I see. Could you program some kind of interesting computation that does a sieve thing? Yeah, I think you could probably write up some kind of program. The state wouldn't be a natural number. It might be like a stream of natural numbers that you're filtering or something like that. But yeah, you could probably do fancier programming than this. Yeah.
So, if you were to create an I tree that had some input I output that gave an actual number and you burned it, what would happen?
Right, that's a good question. So if we had an input natural number and we try to burn it, it will stop and say, the root node is an input. I don't know how to do an input. I haven't said what to do with the environment, so it will give you back the tree. And that gets to the question of, well, what should we do if we want to interpret the nodes of the I tree as something other than just, in some sense, syntax?
Oh, I see. That's
Right.
The viz rule, that's essentially.
The viz is stopping, right? So the result of burn when we hit one of these viz cases just immediately stops. So we'll see in just a minute. I mean, the answer to what we would like to do with input depends on how we're trying to model the system. We're going to write a handler that would maybe explain the meaning of these input operations in terms of some other constructs, maybe like a state monad or something like that. And then we could do running things at a different level. But I think that might be clear as we sort of explore how to build up a semantics for imp. And to do that, I just want to add sort of one specialization of iter, which is all we need for imp, because imp commands don't actually have any interesting internal state. They always return unit. And so all we need from our iterator is whether we continue to go around the loop or not. And we can sort of specialize all of that to just repeat. So this isn't strictly necessary, but it makes the code look nice. And I'm not going to dig into it here. You can also express mutual recursion in a nice way. And if you're interested in that, come talk to me later. But I'm going to skip over it since we don't need it for exactly for imp. So to get to these questions of what if we hit an I/O event or something like that in our tree, well, just as we saw last time where we had this free monad and we interpreted the operations, say, for reading and writing state into some kind of state monad, we can write more or less the same kind of interpreter, or a fold. We can build a fold over the tree in a kind of similar way. So here I'm using the word interp for interpreter because this is what the terminology we ended up settling on for our iTrees library. But the intuition is really the same. It's a monadic fold over the tree. And there's a couple of wrinkles. So what is this? So interp is going to take in, ultimately, it will take in an iTree. It's parameterized by lots of type classes, but the main one is M, which is the monad into which we're going to interpret the events of this iTree. So the idea is, for the visible nodes in the iTree, we're going to give them a monadic semantics in M, and then we're going to fold over the tree and do that everywhere. And this will only work, however, if the monad that we're interpreting into kind of supports loops in the same way that iTree supports loops, because we have to be able to sort of interpret what happens when we have an all towels stream. And so we're going to capture that as a type class that I remember I said, that we call monad inner. And basically that just says it's a monad that supports this very, the iter combinator that we saw back here, except that, we can define this very type where it's generalized instead of over iTree of E, it's over M. So if I rewrite this type as step goes from I to M of I plus R, takes an I and returns an M of R, that is sort of the more general version of this But otherwise, the intuition is the same. So we need a monad into which we can interpret loops. And then actually, writing the interpreter is quite easy. We have a handler, just as the free monad. This tells us for every operation, what is the semantics in terms of M. And then the code for it is actually pretty straightforward. So we're going to take our I tree, and we're going to iterate this body many times. What are we going to do? We're going to take the current node of the tree. We'll observe it. If it's a return, well, we're done. So we will indicate that we should stop with that as our answer, and we return into the monad M that it's a parameter. If it's a tau, we just return. We return into the monad, but we in turn return into the left branch. This version of iter is in the M monad. So this is just saying, if we have a tau, go back around the loop and iterate again and sort of skip past this tau. For a viz, this is where all the interesting work happens. We're going to call our handler on the event. And then we're going to use the fact that all of that our monads are also functors to say that, we're going to restart the loop again with the continuation taken from the viz node of the tree we're crawling over. And we're going to splice the result of that in for the return of this monad. So in some sense, what this is doing is we're invoking our handler to give a meaning to E, and then that's going to give us a result of type R, and we're going to splice in the continuation of the tree we're crawling over as that location in the tree. But we're going to continue to iterate because it's in the left branch. So we're going to go around the loop and keep processing. So this is a little awkward, and you have to maybe stare at it to see what's going on. But intuitively, we're just writing a loop that says, OK, take the first node of the tree. If it's a viz, run its monadic computation, and bind it to the result of iterating over the tail of the computation. And if you have a tau, just go back to the beginning and keep iterating and without doing anything. So we're sort of skipping past the taus. OK. Now, you might wonder which monads support this kind of iterative operation. Which ones can we have iter for? Well, iTree, we already saw, has iter. So any monad that, like we can interpret one iTree into another like this. And it turns out that almost any, if you're familiar with sort of monads in Haskell or something like that, there's a notion of a monad transformer that we'll see use of in just a minute. But basically, if you apply monad transformers to iTrees, almost always they give you something that you can iterate. So functions into iTrees, that sort of thing. And there are others as well. So in Coq, the iTrees library has a bunch of things like that. For the purposes of giving semantics to programming languages, sort of grounding out in iTrees is usually enough. And in fact, there's this kind of special case where the iTrees themselves have no events. So they're only taus or returns. That's the delay monad. And that is sort of, you've handled all the events, and you just have a possibly diverging pure up to divergence computation. Question?
Is there a reason why big R is not used in the
Big R. It is used in some of these underscores where I'm letting type inference kick in. Yes?
If M was another iTree, could we have events that introduce iter? Like, could we have an event with diverge, which just...
Sure. So the question is, if M is another iTree, could we have our interpretation function here internally use iter? Yep, that would be fine. Yep. Good, yeah.
So just to check intuition. So this is very general. You can go from one monad to another. But I suppose in practice you go from an iter with many effects to an iter with less effects?
Yeah, so the question is, this is very general. You can go from one monad to another. But in practice, you go from one with many effects to one with fewer. Yeah, in a lot of cases, that is what you do. In fact, for giving a semantics to imp, that's exactly what it'll look like. But you don't have to. You could introduce new effects. So for instance, you could imagine a transformation that injects logging events or something like that, or adds printing or debugging or events. And that can be quite useful. So you can sort of instrument your sort of tree. You don't have to stay in the same event space. Good. And I just want to point out that this is so general that if we do this, so one monad that you can iterate is what I will call state T of S of I tree of F. So this is this monad transformer. So what state T of S does is it takes a monad and it injects it into the state monad in some sense. It's a state. So if we unfold this type, we get S arrow I tree F of S cross R. So we basically get functions into I trees that return states. That's a very nice semantic domain because it's sort of stateful computations where the I tree also carries the resulting state as part of it. So, but you'll notice that the definition of this interp state is really just the interp from the previous slide because this is already one of these iterable monads. I just wanted to kind of call it out explicitly because we'll use this in our imp semantics just to be very clear about where we're sort of adding state processing. Good. Okay, so that's, so in fact, let's get to that. How do we build up a semantics to imp? And we finally have all of the ingredients, and there are lots of different ways we could do it. I'm gonna pick one kind of usefully interesting way, and that is I'm gonna factor out the memory events of int, so the reads and writes to the global variables as I tree events. This is going to be a nice way to think about it. So what we're going to do is, this is sort of a slightly fancier variant of our get and put operations from yesterday, where all I'm doing is assuming that the events take the name of a string as a location to read, and the write operation will take the name of a string as a variable, which will be the location to write, along with some value. And you can see that when we read, we'll get some value, and when we write a value, we get no interesting response. So we get a unit result. And so this is the signature of the event operations for these trees that can read and write to locations whose names are given by strings, which is what we'll need for imp, because the variables in imp are, well, we can represent them as strings. And we can make little trees out of these using our trigger. So just to make things look pretty. So read of x will be this little tree that just corresponds to the read event. And write of xv will just be the little tree that has the write node at the root. Okay? And now we revisit the way that we wrote the interpreter for imp in the first day and do it with I trees instead. And again, there are several. We already know that the arithmetic expressions for imp are pure. But the way I've set things up, arithmetic expressions in imp can rely on variables like x. You can say x plus y as an arithmetic expression. And since I'm going to say that reading a variable, reading a location is an effect, that means that we can't, at some level, we're going to have our arithmetic operations are not going to be pure anymore, at least not until we interpret the read events. And we'll see exactly what this means in a minute, but to a first approximation, what I'm going to do is recognize that we have plus minus multiplication events, give them a denotation in terms of arithmetic. So add, sub, and multiply are the natural number to natural number operations corresponding to those. And here is what our interpreter for arithmetic expressions looks like. It's a bit of code, but I've factored things so that It's a little bit modular. So let's read through it. So this is our syntax, our arithmetic expressions. Notice that the return type here is an I tree whose events are drawn from these memory events, and we're going to compute a value. Here, val is just a synonym for a natural number. I separated it just because we have lots of natural numbers floating around. So let's see some easy cases. So if our syntax is a literal constant natural number n, well, we just return it. It's a pure computation. If it's an ID, so an identifier like x, well, here, we're not going to necessarily think of this as pure yet. We're going to build a little tree that says, we're going to read the value of x from the environment. We haven't said anything about how to interpret it yet. Notice that this version of the semantics, unlike the other one, isn't parameterized by a memory, right? So I could have done that. I could have just used the old one where we have a memory, and then I wouldn't need to use this trick. I wanted to kind of illustrate the kind of design space here. So we're not saying what it means to read from a memory yet. We're just saying that this builds a little tree that has a read event in it. And for plus, minus, and multiplication, well, they're all very similar. They're binary arithmetic operations, so I factored that out into this little helper function. So to interpret, say, one of those operations, we're going to recursively denote the left-hand expression, A. We'll recursively denote the right-hand expression, B. Notice that we're just using monadic bind here. And then we're going to return, this is the actual arithmetic value. So in some ways, you can think of this as, because our I trees in this case are returning values, which are just natural numbers, when we denote A and denote B, they will be I realize I shouldn't have overloaded A so much. This should be op left and op right to make it a little clearer. And then we just return the result as a natural number. So we're building up a little tree. And if in some world the order of evaluation mattered, here is where we would explain that, because this is doing left to right evaluation for the left hand of the operand and the right hand. Afterward, we can see they're sequentialized by the monad here. Of course, since this will ultimately end up being pure, that doesn't matter, the choice of ordering. We could prove that it doesn't matter, in fact. OK? So that's how we write an interpreter for arithmetic expressions. It's a little variant on what we wrote on the first day and using I trees. We can do the very same thing for Boolean expressions, Boolean operations, so I'm not going to dwell on it. I imagine you can see it's literally the same style. We just bind the operations. We sort of are writing an interpreter where this is the result type instead. So commands are where the interesting action is. And this I'm going to factor into two cases. So I'm calling this the representation of a command as an I tree, right? So what we're doing is we're taking our abstract syntax and converting it into an I tree that has these read and write events in it. But we haven't said how to interpret those read and write events yet. But that's OK. We'll do that next. So for skip, and notice that here, all of our commands will return unit as a result. They don't actually have any interesting answer as computations, but they do generate these memory events. So skip is actually quite trivial. It's just return the unit, the only thing you can possibly return. Assignment is interesting. We have our interpreter of arithmetic expressions, which uses I trees. That's of type I tree mem-e val. And so we can name the val, interpret the arithmetic expression, and then write that value to x. This is the little helper build a tree node. Sequential composition is really nice because bind is sequential composition, and we can have a little helper double semicolon without the left arrow means underscore left arrow. So you can ignore if you don't care about the result, you don't even need to name it. So you can write a very clean interpretation like that. If then else looks more or less like what we saw before. We're going to interpret the Boolean expression B. That will give us a Boolean value. The interpreter for bools will give us a coq bool. And then we can write the continuation in coq. So here's where we're doing this shift from abstract syntax to meta level. We're using a continuation that has two different results. So this is saying that if B is true, in the true branch of the tree corresponding to this, we're going to have the subtree called C1, and otherwise it'll be the subtree C2. And here is where all of our work for iTrees pays off, because while is extremely easy. I could have made a little more syntactic sugar, but we just call into our repeat combinator. What is the step of a while loop? Well, we check the guard. We name it x, so that's going to be a Boolean. We check the conditional. If x is true, well, then we run the body and return. This is basically signaling to go back into the loop, to jump back to the top. So I could have made syntactic sugar for continue or something like that, but spelling out the go left back to the top. And otherwise, this loop is done, and so we just halt, or we exit the loop with the in right. And that's all there is to it. So we finally sort of packaged all things. What I really like about this, in contrast to the operational semantics that I showed you on the first day, look at the definition of while here. Its meaning, so here's the concrete syntax. And I have called these representation functions completely structurally on B and C. And then I kind of plug them into a combinator. But I didn't have to do anything interesting to process C. I just did induction on the, I wrote this. Notice that this is just a regular old fixed point operation. It's inductively defined on the structure of the syntax of a command, and we're just doing structural recursion here. And that's fine. It just gives us a tree that we plug into our very fancy iterative combinator. And that is going to make proofs over this work by induction on the structure of the syntax instead of induction on the derivation that they evaluate or something like this. Of course, we'll have to be able to reason about these repeat and iter combinators to make that useful. But that's fine. We've sort of separated reasoning about looping things from what the loop bodies are going to do in a nice way. OK? So the other thing that is still true about this is that it's parametric with interpretation of the memory events. I still haven't said, what do these read and write things do? And that means that if I wanted to, I could use this tree with some other meaning for those read and write events. Like I could add logging or maybe some kind of security instrumentation. Or I could just implement the standard semantics. And those would be different interpretations of the same tree. And it's still compatible with extraction. We can write, if we extract this from OCaml, in OCaml, this just becomes a recursive function that builds one of these co-inductive trees. OK. So another way of thinking about this is these trees are in some ways still syntactic. They still have these read and write events in them. But we've sort of unfolded all of the control flow, right? So the if branches in the syntax, like up here, have become meta-level ifs. And the while loop has become this repeat combinator, which sort of is building a cyclic tree. So we've sort of unrolled all of the kind of control flow structure. And the consequence of that is that there are going to be things we can prove, like equivalences on imp programs, that will be true regardless of how we interpret the memory events. And we could prove them at this level instead of at some other level of interpretation, which is kind of nice. It'll be sort of, no matter what your memory model does, these equivalences will be true. And those are typically things like loop unrolling, right? So that doesn't have any interaction with the memory model. OK, good. So any questions about this? So what we've done? Yeah.
Can you also make it parametric in the semantics of the operations?
The question was, could we make it parametric in the semantics of the operations? Sure, we could. Like the arithmetic operations, we could also make a parameter here. And this is where the design decision of like how much do you parameterize and how much do you specialize is kind of a big design space. And maybe it depends on exactly what you're trying to do. But and here I didn't make events for like the arithmetic operations, for instance. But you could. It would make perfect sense. Yeah. Good. OK, so let's see now how to finish this semantics. It's not too hard at this point. We just have to say, what are the meaning of the read and write events? That's kind of the only missing piece. And we already saw basically that. So this notation that I'm using up here for this, the monad that we're going to interpret as the target of our semantics is going to be state T, where we've specialized the state to imp memories for compatibility with the old semantics. But we could make a different choice there if we wanted to. And there will be trees of void here. Void 1 is sort of the type that promises no constructors. And so what tree of void basically rules out the viz case. So there are no constructors for viz nodes. And so the only constructors of this kind of tree are tau and return. And so this is the delay monad if you're looking at the literature. And so if you kind of unfold this definition, the final semantics we're going to get are functions from imp memories to delayed computations of memories paired with unit, because commands return unit. So morally, it's sort of memories to memories, but you might also go into an infinite loop and never halt. And to get all of that, we just need to say, well, the read event, how do we implement it? Well, it's a version of the get operation we saw. If the current imp state is st and we read x, well, we just look it up in the state. And if we write x, the value v, then we just return the update. We end up in the updated state where we've changed x to v, and there's no interesting result. So this is the entire memory model for imp right there. It's just, and we could change the semantics by changing these functions. And then finally, this is kind of maybe anticlimactic. The final semantics is, well, we use the interp state. That's that interpreter function. We use the handle memory. That's it. That's the denotation. And that has the type. Well, we can now kind of eta expand it and say the model, the semantics for one of our commands is, well, give me the command and pass it to this interp state of handle mem. And then we write it in some nice denotation brackets to make it look more like denotational semantics. And the result of that is m of unit, where m is, m of unit is exactly this, right? Okay, so that's the semantics. And now we have an executable semantics in some sense that has the state interpreted properly. We can use our burn thing to also compute here. So we can compute this fact. So fact in coq is the abstract syntax for our factorial function that we started with. And if we run that starting from the imp state where everything is 0, well, and we give it enough fuel, it will end up in a state that looks like this. Although I'm cheating a little bit here because the way coq prints these functions, that pattern match on strings is really hideous. So if you run it in the environment, you'll have to stare at it to see. But we could prove that the resulting function is extensionally equivalent to this one, at least. But that's not so exciting. What we'd rather do is prove equivalences based on this semantics and maybe do other meta theory things like justify the correctness of type systems and that sort of thing, or other kinds of program logics. So that's what we're going to get to next. And if you're curious, a really fun thing you can do is add a print or IO events to imp and see what changes on all of this. So the result would be, instead of one nice thing you could do is just not interpret print events. And then you end up with a tree that has potentially print nodes as part of it, but otherwise looks the same as before. And you can read off the trace of what gets printed to the console by thinking of that as And then you could write an interpreter for print that appends them to a log or something. And there's interesting things you can do. But the nice thing is none of the semantics needs to change very much at all. You just need to add the handler for print. Good. OK, so any questions about that? Where I want to head next is reasoning about both iTrees and IMP programs. Yeah?
I'm trying to have some intuition for what iTree void 1 means.
Yeah.
Is that like should I think of it as like, this is a pure value?
Right, so iTree void 1, I can show you exactly what it is if I switch over to iTrees. iTree void 1 is the data type that you get if you just cut out the viz node. Because void 1 is the empty E, so there cannot be any E's that you would be able to use. So it's literally a co-inductive data type where you have a base case for return, and you can co-inductively have tals. So it's either a spin, infinite number of tals, or some finite number of tals followed by a return. That is a monad. That's particularly called the delay monad, and it's what you would think of as pure in any language, like even Haskell allows non-termination as an effect. So it's pure in Haskell, I guess is one way of thinking about it.
But it does diverge.
It can diverge. It might diverge. Yeah. Good. OK. Good. Any other questions? So we already have most of the machinery that we need to reason about iTrees because they're monads. They satisfy all the monad laws. You might ask, what are the sort of special equations justified by the fact that we have this particular monad as opposed to an arbitrary monad? And the way we do that is, we have to first, prove an equivalent or provide a definition of equivalence for monadic computations so we can justify the monad laws. And then we can use those extra equations up to these equivalences. And so the right equivalence, so we might ask, what is the right equivalence? And it turns out that there's a couple of good answers. And one of them is what's called a strong bisimulation. So because the iTrees are these co-inductively defined data structures and can represent infinite trees, the definition or the notion of equivalence you want is also co-inductive. So this is a bisimulation is such a thing. I'm not going to dwell too much on it, strong bisimulation. All you really need to know is it's basically what happens if you imagine the process of unrolling the iTree to infinity, so sort of building the full tree forever. And two such trees are considered strongly bisimilar if they have exactly the same structure, tau for tau, node for node, branch for branch, and it's extremely strong. Yeah.
Why not weak bisimulation?
Oh, that's going to be next. And the reason, that's I'm only being a little facetious about that. So strong bisimulation is useful, and in fact, all of the monad laws hold up to strong bisimulation. So that's quite nice because strong bisimulations are usually pretty easy to work with because they're strong. They tell you very rigidly if you have two things that are equivalent, they're going to have exactly the same number of tals, and that makes certain kinds of proofs very simple. And it turns out that all of the monad laws, bind associativity, return, and left, and so on, do hold up to this notion of equivalence. So that's great. But you might ask, why we might want something else, and this is the weak bisimulation. So here are two trees. This is the same tree that I showed you before. Make this a little small. Here is a very similar tree where I've sort of cut out many of the tals. In fact, I've sort of tried to cut out as many as I could. I can't get rid of an infinite stream of tals because that is semantically meaningful. That's an infinitely diverging, a silently diverging program. But any sort of finite number of tals between events, we could ignore. And certainly we could sort of ignore any finite number of tals before we get to the root of the tree, for instance. But we could also, ignore a bunch of tals in between these visible events. And so if you sort of strip out as many tals as you can, and what I mean by as many as you can, It means that at any point in time, co-inductively, you can strip out any finite number of tiles you like. And then if you hit one of these visible events, you can co-inductively do that down the infinite rest of the tree. That's maybe a little counterintuitive. One way to think of it is you can just ignore tiles unless you happen to be following an infinite number of them. So this is called weak bisimulation. And it's weak exactly because, well, many, many more trees will be considered equivalent. Like another way of thinking about it is if you take one of these trees and you sprinkle more tiles in, that's still going to be equivalent. But only inductively many more tiles. You can't sort of add a diverging computation where there wasn't one before. So this notion of equivalence is the hard part of formalizing I-trees. Technically, you have to use what's called a nested co-inductive inductive definition. It's co-inductive kind of to crawl over the tree forever, and at every step you can sort of crunch down an inductively many finite number of tiles. And if you do that sort of maximally, you get this notion of equivalence. And if you go to all that trouble, I'll use double equivalence. This is sort of this is the one that we use as the default monad equivalence for I-trees, even though strong bisimulation does respect the monad laws. It's usually, if you want I-trees, you probably want weak bisimulation. So we use this as the default notion of equivalence for our I-trees. And the equation you get after all of that work is basically tau of t is equivalent to t, which seems rather modest after all this work on defining these inductive relations. But it really, if you think about building a proof out of this, proofs are finite things. You're going to be doing them with induction. You can only sort of use this premise or premises like this kind of inductively many times. And so you can sort of ignore, and if any time you see a tau, you can ignore that one. It's fine. As long as you don't keep doing that forever, you're in good shape. And we call this in our paper equivalence up to tau because you sort of can add taus or remove them whenever you like. And of course, strong bisimulation implies weak bisimulation. You can ignore zero taus. And so if you can prove strong bisimilarity, then that implies this question.
So does weak bisimulation respect the monad laws?
Yes. Yep. Weak bisimulation also respects the monad laws. And in fact, we get more laws, which is why we want it. In particular, I think we get laws for the iterator combinator. So the thing we could do, we couldn't do in general monads, and we couldn't do in the free monad, but we can do in I-trees, is write iter. And most of the so remember when we went around the loop for iteration, we had this tau guarding our kind of back edge in the jump. And that's the one we want to kind of ignore for the purposes of equivalence, because it's an internal step. Jumping back to the loop is sort of not something you really care about from the point of view of program equivalence. And so, for instance, here is what you might think of as an unrolling law for iter that says, well, if I'm iterating some step body starting from I, well, I can unroll it once by running the body, and then looking at the result, and if it tells me to continue iterating again, and otherwise returning v. So this is not true up to strong bisimulation, but it is true up to weak bisimulation. So you can just, and I should say, anytime I'm writing these laws like this, what it means that in Coq, we can use rewriting as a tactic to convert this kind of program into this kind of program. And so now you can see how we could sort of proceed by thinking about how a program steps by unrolling the loop once and then maybe figuring out what particular step it's going to do and proving something about that and so on. So that's one law, but there's actually a whole bunch of others. Oops. Some people were asking about Kleisli categories. I wrote these laws using the Kleisli formulation because they're a little bit prettier, but morally, I think you'll see what's going on here. You get these sort of equations that say, well, if you're iterating a step this is actually the law I showed you on the other side written in this notation. If you're iterating some step, that's like doing the step and then deciding whether to iterate again or end with the identity function. So this first bullet here is just a sort of category theoretic reformulation of this law. So what it buys us is we don't have to quantify over the I and sort of write these point-wise pattern matches and things. And there's some nice, so if you're iterating a step and then after you iterate, running some continuation, well, this is a little funny. This is saying, well, you could iterate the step, and in the case where you end, you could directly jump to the continuation. And this is maybe a more interesting one. It says if you're iterating an iterator, well, you can iterate, unroll the inner iterator one step, and then decide whether to go back. So this is actually, notice that this one is fusing two iterations into one. So this is kind of a loop fusion law that you can prove just from the weak by simulation. Good. All right, so that gives you a sense of the extra equations that are justified by this approach. And now what we want to do is kind of apply all of that in the context of one of our, for example, our IMP denotational semantics that we just built a little bit ago. And here I want to point out that what we kind of did is we started with abstract syntax, very concrete inductive data types. We had this repr thing, which created an I tree with memory events. And then we interpreted that with the state handler to sort of eliminate the memory events and turn them into the state monad operations, where we now are sort of left with the delay monad as the result. And the point is that actually different equivalences hold at each of these levels. So syntax is very rigid. We probably just have literal equality for IMP programs at that level. But because at this level we've unrolled all the control flow, there are quite a few equations that hold at this level that we can prove without having to worry about all this divergence and non-divergence, or even what the semantics of memory operations is. So this is sort of reasoning you can do parametric in the memory model. And then, of course, there are some properties that depend on the way we implemented the memory model, and those will only be true down at this level. And you can kind of stratify things, and that's quite nice because then you can choose a level of to work with. So one thing that's a little bit complicated in this part is there are lots of, so we have three kinds of denotations for IMP. So we have three notions of equivalence, for different stages. We also have arithmetic expressions and Boolean expressions that we could also interpret at each of these levels. So we have sort of equational theories going on at the arithmetic level, the Boolean level, and the command level. So 9 equivalence relations. And so it gets a little overwhelming, but none of them are too unintuitive, right? So we have like syntactic equality, representation equality, let's call it semantic equality. And then I'll try to use like subscript A for arithmetic, subscript B for beta for Boolean equivalence. And maybe the most important ones are sort of equiv and approxiquiv. These are sort of representation and denotation. But if you just kind of think of these as equivalent, these are all equivalences, and so we have to be particular when we're proving things, but intuitively, you can just read them as equals. And so one nice thing is that we can, prove lots of the facts that we already saw in terms of IMP. So, all of these different equivalences are actually equivalence relations. If you have another thing I should have mentioned is that an equivalence at one level of this higher interpretation stack implies an equivalence at the lower level. So it's sound to do, think about interpreting two equivalent things at this level will still be equivalent at that level. So our interpretation preserves equivalence by the way we've defined things. And then we also can often prove, and like you would want to do this in practice, is that most of the equivalences are congruences with respect to the syntax, so you can build things compositionally. And in the Coq development that I provided, I go into all of that in quite a bit of detail. It could be a bit tedious here, so I'm just going to kind of give you a sense of the idea in the last 10 minutes. But so there are a couple of interesting things we can do. So first, we can prove something about just the memory model without any reference to imp at all, which is kind of neat because we're factoring proofs about the memory model from proofs about the semantics. And so, for instance, one thing we can prove is that if we interpret these read events, well, in this semantic model, that's equivalent to a function that, given some initial store sigma, ends with a computation that returns the store unchanged and gives us sigma of x as the result. This is just basically what you would expect as the definition of this read operation. But and similarly for write, so the fact that we can prove that this is EUTT, equivalent weakly bisimilar to return, well, return is pure. So there's a little bit of work going on here. We're saying that, with respect to these I trees, there aren't any other events being introduced by the memory model in this case. So they're pure events. That might not be true if you had debugging or if you had a memory model that injected some other kind of events into the semantics. And similarly, we had this arithmetic evaluator that I showed you on the first day, this kind of straightforward vanilla in Coq inductively defined function on natural numbers. Well, we can prove that when we run that, use our denotational semantics on this arithmetic expression with this particular state model, this particular implementation of the memory, well, that interpretation is also pure and gives us the same answer as sort of our Coq specification does, right? So we have a functional pure specification. We have an implementation in terms of these events and a handler. And we can prove that this side is equivalent to that side. And similarly for Booleans. So that means that we can interchange calls into our semantics with calls into our Coq's functional specification, which might be useful and easier to prove things about. And then, as I was saying, we can sort of stratify all of our equivalences into different things. So I'll just flash a few ideas here. So this is things we can prove without understanding the semantics of the memory model, right? So here's a bunch of them. And so this is a bunch of them. Let me just say one thing. The reason, so I'm characterizing these as equations. The idea is this is just a Coq data type where each constructor corresponds to an equation that we might want to apply in an optimizer. And for instance, we might want to optimize 0 plus a into a. And the idea is we're going to write a little data type that enumerates rewrite rules, basically. And then we can prove the correctness of each of these rewrite rules with a little lemma that tells us that the meaning of this side is equal to the meaning of that side. And then we can write tactics of the kind I already demonstrated on the first day, where that sort of uses these kind of enumeration of rewrite rules to search through how to apply them interestingly on imp programs, for instance. So we could write a program that looks for occurrences of this syntax and replaces it with that syntax. And the correctness will be justified by proofs that we have to do, but that can be completely automated so that we can use them in a tactic-driven way. So all of these rules are just about arithmetic expressions. They make perfect sense. Here are a bunch of them about Boolean. Not true is false, and so on. You can think of these as rewriting optimizations that apply. And then we can get, here are a bunch of commands that are true not only up to independent of the memory model, but don't even need anything with iter. So these are strongly bisimilar rules. So skip followed by C, we can drop the skip, for instance. So in the denotation, skip doesn't even appear as a node in the tree, so there's not even a tau for a skip, which is kind of interesting. Similarly, we can remove a skip from the other side, and so on. So we can sort of, oh, here's associativity of imp commands at the syntactic level. That just follows just literally straightforwardly from the associativity of bind at the I tree level. We don't need to go into the monad interpretation. And so on. So we have a list of, here's basically the while loop unrolling for imp. This one is also true. It doesn't need EUTT. So we can unroll the loop once, and that's equivalent to this while. And then there are a few that are a bit trickier to prove, but are still true. So for instance, while true do C, we could optimize by throwing away the body of the infinite loop. So while true, we can replace this program with that one. And this is sort of another loop unrolling, but it's unrolling the loop from the inside instead of from hoisting out the command. So it's sort of putting a conditional check at the end of the loop body. I don't know why you would really want to do it, but you can. And this is also valid. So yeah. OK, and then as I said, what we do is for each of those little rewrite rules, we do a little proof that says that they're sound. And most of the proofs are pretty straightforward. We're using this pure, that pure thing. They're really pretty straightforward, right? So here, norm is our tactic that sort of tries to normalize a I tree, pushing forward the evaluation. So we don't have to really reason too much about evaluation to do these. Here, for example, here's the proof of skip followed by C is equivalent to C. Very pleasingly simple. So some of the proofs are a bit trickier. Some of the loop equivalences especially need tricky invariants to say that you're not sort of doing bad things when you unroll the loops. And then basically what you can do is for each of those branches in our sort of data type, you can prove a theorem that says if you can rewrite A1 to A2, then it's sound. So this is like a general purpose proof for all of the cases that we enumerated before. And similarly, we can do that for Booleans and for commands. And we can prove commands for two different sort of strong and weak notions. And once you have that, you can plug them into, you can prove program equivalences with a tactic. So for instance, this is not a very exciting program. It just replaces x minus x, let me see, with 0. It proves that if you assign y 0 here and x minus x here, these are equivalent programs. But this is the proof of it. And that's actually non-trivial because this is using a lot of congruence to sort of dig down to the part of the proof where that x equals x minus x occurs. And you have to prove that all of the surrounding context is equivalent. So it may not look super impressive, but being able to automate these kind of proofs is quite nice. And then you can, so these kind of proofs is just a Coq assertion that says this program is equivalent to that one, and it's proved by this tactic. That's not quite the same thing as an optimizer, which takes a piece of syntax and provides another piece of syntax, which is supposed to be equivalent, and then a proof that that optimizer is correct. But of course, with these tactics, you can do that too. So I showed you at the beginning, so this is constant folding as a tactic, but I showed you at the beginning that we could write a program transformation as an optimizing function. And here is, it's a little bit ugly because the fold constants x is long. But this would be essentially a little constant folding. So for instance, if we have two concrete numbers and some arithmetic operation, we do the operation statically. That's what this is doing. And so we can write a little syntax to syntax transformation. But what's quite nice is the proof of correctness is just a very nice straightforward induction on the structure of the syntax, where you sort of appeal to rewriting using this equational theory that I just showed you. Okay, so let me fold this back up. And you can use it to prove that these things are sound. Good. Okay, so actually that's a pretty good place to end for today, since we're at the end of the time. Any questions about that before I wrap up? Okay, so the plan for next time is, oh yeah, sorry, was there a question? Yeah.
I was wondering, if we have like an iTree void, is there any way for us to escape iTree? Like, can we prove?
Is there any way to escape iTree? So this is not just true of iTrees. It's very hard to get out of monads in general, right? Once you've entered the monad, you can never leave. Some monads do support a run operation, like the state monad. You can have a run state function. But iTrees, at least within Coq, you cannot escape the monad. That's not completely true. You can write an interpreter. I mean, you can write an interpreter into some other monad with an iterator. But if you just have an iTree or delay, no, you can't. Good. So the plan for tomorrow will be to do some more reasoning about this, and then I'll, given some time at the end, I'll show you how we kind of give you a taste of how we're using this in this verified LLVM project. And I'll see you then.